Hi, this is Mathematics for Social Justice by Mark Roth. Today we're going to set up a rapid calculation trick which a teacher could use with students in a classroom, or you could show it to a friend. Let me try to explain it. We're going to be working with the numbers 1 through 24, but not all of them. A number like 3 over 24 can be reduced to 1/8. So it turns out that 3 and 24 are not relatively prime. And that basically means that they have a number other than 1 that goes evenly into both of them. So they have a common factor other than 1, so they're not relatively prime. We're going to try to get rid of all the numbers in this chart, 1 through 24, that are not relatively prime to 24. So first of all the even numbers, if you wrote the fraction an even number over 24, you could always reduce. So these 3 columns here have all the even numbers, and we can eliminate them. So that leaves these multiples of 3, and any of these over 24 could be reduced. So if we eliminate those, we end up with 8 numbers that are less than 24 that are relatively prime to 24. So this Greek letter phi is often used. They say 5/24 is equal to 8, which tells you that there's 8 numbers less than 24 that are relatively prime to 24, and here they are. And one way to calculate that is start with 24 and times by 1 over 1 minus 1/2. And that's what we did. We took away half the numbers, and then we took away a third of the others, because then you go 1 minus 1 over 1/3. So it turns out to be 24. 1 minus 1/2 is 1/2. And 1 minus 1/3 is 2/3. So if you do this calculation, 24 times 1/2 is 12. 2/3 of 12 is 8. And you end up with the 8 numbers that are relatively prime to 24, but less than 24. And these 8 elements give you a group, U24. It's a commutative group, or a abelian group. And groups basically have an identity element. You have closure. Anytime you multiply any of these 2 numbers and then subtract the biggest multiple of 24 that you can, you end up with one of these back. For example, if you go 7 times 11, you get 77. Here I have the multiples of 24 up till 528. So if I take 77 and I subtract 72, I get 5. And that's one of the numbers. So that's closure. Anytime you times 2 of these together, or one of them times itself, you get closure. You get one of these back. And that's part of the characteristics of a group. Also, we have associativity, and that just comes from these big numbers. And we have an identity element, which is 1. 1 times anything gives you the same thing back. And every element has an inverse. We're going to put these numbers on the corners of this cube. So let's try putting 1 here. And I'll go ahead and put 5 here, 7 here, and 11 here. It's going to be a little bit of work placing the other numbers, but I'll show you how I want it done. So I want this number and this number. When you multiply them, you get -1. Now, we're actually operating on a clock that has 24 numbers. So imagine a clock with 24 numbers instead of 12. So you have 0 here, and you have 12 here, and all the other numbers. But this number here is important. It's -1, which is also 23, and this is +1. I want this number times the opposite corner to be -1. And -1 is equal to 23, so I'm going to put 23 here. I'm going to do some calculation now. So I want to find out what's going to be opposite 5. So 5 times what is equal to -1? Let me set that up. I want to solve this algebraic equation. 5 times x equals -1. X is equal to -1 over 5. And I can change that to 23 over 5. So on the clock, every time you add 24 to a number, you get the same basic number. They're in the same class, same equivalence class of numbers. So I'm going to keep adding 24 to the numerator until I get a number that 5 goes into evenly. So 23 over 5, if I add 24 to 23, I get 47 over 5. And if I add 24 again, I get 71 over 5. If I add 24 again, I get 95 over 5. Okay, so that goes in 19 times. So opposite 5, I'll put 19. I want to know what's opposite 7, and I'll put that down here. So I'll do the same thing. 7x is equal to negative 1. So x is equal to negative 1 over 7. Okay, so change that to 23 over 7 by adding 24 to the numerator. And then 47 over 7. And then 71 over 7. And then 95 over 7. And let's see if, I don't think that goes in evenly. That's going to be 119 over 7. Okay, that goes in. So that goes in 17 times. So that means 17 is going to go opposite the 7. So that's 7, that's going to be 17. So I only have one more number. So the only number left is 13. Now, we're all set up and we can do the trick. So this trick is based on this previous activity called Go to the Red Room. If I'm at 5 and you tell me to go to 11, I go to 7. And how did I do that? Well, first of all, there's a quick way to do it. So basically, 1 is the special point. And 1 and 5 and 11 together with 7 give you the front face of the cube. So all I have to do is say, okay, 5 times 11, find 1, and find what makes the face of the cube. But let's make sure it works. 5 times 11 is 55. 55 take away 48 is 7. But the thing is, you can keep this secret from the students, and you can amaze them, or if you're doing it with a friend, just amaze your friend. How did you do this so quick? 5 times 11 is 55, and 55 minus 48 is 7. You're doing that really quick, because you're just spotting it. Now, so you do that with the 6 faces. So for example, suppose I'm at 19 and you tell me to go to 23. I go to 5, that quick. Because basically what you're doing now is not a face of the cube, you're doing a diagonal slice of the cube. You're basically, pretend this is like a cube of cheese and you're slicing diagonally through the cube of cheese. So you're covering this, 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 and this, and you come to 5. So let's make sure that works. So if we do 19 times 23, so we get 437. 437, take away 432 is 5. So basically you're doing this rapid calculation, but you got a trick. You're just basically doing it with a visual. There's actually 6 faces of the cube, but only 3 of the 6 faces go through 1. And there's actually 6 ways to slice diagonally through a cube, but you're only using 3 of them because only 3 of them hit this corner. And then there's a thing called an inscribed tetrahedron. It's like a crisscross. So this, and this, and this, and this. Think of it as a crisscross. You're going like this, and then you're going like this. So if you told me, if I was at 19 and you told me to go to 11, I would go to 17 because I'm doing this inscribed tetrahedron or this crisscross. So I'm spotting 19, I'm spotting 11, then I go to 1, and I think, okay, this and this. So that's one of the inscribed tetrahedron, or what I call a crisscross. So let's do a couple of examples. Suppose I'm at 7, and you tell me to go to 11. Okay? Now, I don't have to do the calculation. All I'm saying is 7, 11, and 1 will take me to 5. Okay? Suppose I'm at 19 and you tell me to go to 17. If I'm at 19 and you tell me to go to 17, it looks like that's a crisscross. We have this crisscrossing with this, so that's going to be 11. Okay? Let's go ahead and check that one. 19 times 17 is going to be 1 less than 18 squared, so it's 1 less than 324. It's 323. So go down to 323. So 323, take away 312 is 11. So is that what I said? I said 19 and 17. That's part of this crisscross. And I said you would go to 11. Okay? So it's this crisscross, or this inscribed tetrahedron. Let's do one more example. Suppose you want to do 7 and 23, okay? So if I'm at 7 and you tell me to go to 23, I'm basically doing this diagonal slice. I'm slicing like this. It's a diagonal slice to the cube, and I go to 17. So 7 times 23, let's verify that with multiplication. That's going to be 140 plus 21, that's 161. 161, you take away 144, it's going to be 17. That's what I said, right? So 7 and 23, 1 and 17. So again, you have 3 faces that include this corner. You have 3 diagonal slices that include this corner, and 1 crisscross, or inscribed tetrahedron, that include that corner. And with that, you can do this trick. So to conclude this video, we can transfer this information to a final plane, which is the smallest finite projective geometry. So we can start by making a triangle, and then draw these lines, and finally make a circle. And where the cube has 8 corners, this has 7 points. So we have these 3, and these 3, and this point here. We're leaving out the 1. Now it turns out, when we were looking at this like bottom face, we had 3 numbers plus the 1. Well, we'll leave the 1 out. Let's try putting 5, 13, and 17 down here. And this is 1 line. And then we have 6 more lines. The last line would be the circular line. We think of lines usually as being straight, but this last line is circular. We could go ahead and put, let's say, we could put 23 here. So now we want to complete the line that has 23 and 13. So here's 23 and 13. It looks like if we do this diagonal slice, it'll include 11. So 11 has to go here. And now we want to complete 5 and 11. So here's 5 and 11. So 5 and 11, the front face would be 5, 11, 7, and 1. We always want to include 1. So 5, 11, and 7. And let's double check that 23, 17, and 7 is on here. 23, 7, and 17 is going to be a diagonal slice that goes from here to here. It's like slicing through the cheese like a diagonal slice. So 23, 7, and 17 is good. So now we want to complete 17 and 11. So 17 and 11 and 1 is a crisscross. So we have 1 and 17 crisscrossing with 19 and 11. So you can also call that inscribed tetrahedron. So that's going to be 19. Let's just double check this one here. Make sure 5, 19, and 23 are good. So 5, 19, and 23 would be a diagonal slice from the top back to the front. So it would include 19. So this completes the final plane. And now if we multiply any two numbers like 17 and 13, we should get 5. So 17 and 13 is 4 less than 15 squared. So it's 221. And 221 is 5 more than 216. That gives us 5. So in other words, when you get 221, you subtract the biggest one of these you can, which is 216, and you get 5. Let's try 17 and 11. So 17 and 11, that's 187. You find 187, and you subtract 168, and you get 19. Okay, so 17 and 11 gives you 19. Let's do the circular one. If you go 7 times 19, that's 133. 133 over 120 is 13. So it turns out the math of the cube transfers to the math of the final plane. We'll end the video there, and thank you for watching.